Was the attendance passed out?
Not yet. I shall pass out in just a moment. Okay, attendance sheet is going around. I believe what I have on the board is where we left off last time. Can somebody corroborate for me? Is this true? Yes? So we were doing spring mass vibration. Okay, we had a forcing function F cosine omega t. Okay, and so just to recap on that, okay, the first problem we had solved was no forcing function. Just perturb this thing and let it go, right? And when you do this, the right-hand side of the equation is 0, right? And we realize that, you know, the frequency of oscillation is the part that's in the transient solution, root k over m times time. Okay, and now we said, well, what if I have a mass here, okay, and instead of it just freely vibrating like this, what if I grab it and I vibrate it, you know, with some other frequency, okay? And that frequency is omega. That could be any number, right? And as we developed this steady state solution last time, we said this is what the answer is, right? As long as this denominator right here wasn't going to be 0, okay? And if you take a look at this denominator, k minus m omega squared, what would be the omega that would make the denominator 0? So this is as long as the denominator is not 0, which would be what? Square root k over m, right? Note that square root of k over m is this one. Okay, so as long as I don't force it at exactly the same frequency, okay, as what the natural frequency is if it vibrates freely on its own, okay, if I don't force it there, then I don't run into any math problem when I solve for those constants. And so this is as long as omega is not exactly equal to root k over m. Okay, every other possible value of omega, this works for the steady state solution. Okay, we will take a look at what happens, you know, as I approach root k over m when we get the final answer. All right, so I think we left off there. So the question for you guys is steps 1 and 2, transient solution, steady state solution. What is step number 3? Add them together. Okay, so step number 3 is the total solution, right? Total solution. Okay, and yeah, I got to add them together, right? So y of t is always going to be the sum y transient of t plus y steady state of t. Okay, and so we'll add those guys up. So I've got, you know, at this point, the following. Y of t, the transient part is c3 times the cosine I've got a root k over m times t, plus I got c4 times the sine root k over m t, plus I've got the steady state, which is f divided by k minus m omega squared, okay, times the sine omega t. Okay, so I've got all of that stuff as the solution at this point. Okay, and so the question to you guys is, what is still unknown in that total solution? C3 and C4. Okay, these constants that come up in the transient solution are always unknown at this point, and in order to solve those, I have to apply the what? Okay, apply the initial conditions. So again, in general, the homework problems that are already posted, right, you guys have had since before Thanksgiving. I'm sure you guys all just turned off football and you just stayed home and worked these problems. Okay, but if you didn't do that, then those are still there posted, right? The homework's due Friday. And when you're working through these problems, you realize generally at the problem statement, we got the governing equation and we've got the initial conditions. Okay, and so here's our governing equation. Here in lecture, I like us to kind of think about at the appropriate time, what are the appropriate initial conditions? Okay, so the free vibration problem, right? Here's the statics problem. And we said the dynamics problem is now displace it and let it go. Okay, and so those initial conditions were a non-zero displacement, right, an initial displacement, and then 0 for an initial velocity. Okay, so if I apply a forcing function, f cosine omega t, do I need to have any initial displacement in order for this thing to vibrate? I mean, I could, but suppose I start right here, okay, at t equals 0. I've got nothing. No initial position, no initial motion, no velocity. If I now apply f cosine omega t, is this going to move? Yes. Sure. Right? I mean, it's in equilibrium right now. It's at the equilibrium position. If t is greater than 0 and I apply that force, in fact, I'll get instantly at t equals 0, I'll get a force of what? The force is f cosine omega t, so at t equals 0, what's the force? F. So it's like immediately I have a force, right? And then that force oscillates. Okay, so yeah, absolutely. I can start with nothing and I can move it. So we could put whatever sets of initial conditions we want. I could apply a force to something that's already moving, right? Something that's already displaced, but why not just go with the simplest case? It doesn't have any initial position or velocity, but it is going to have a force. Okay, and so the force is not an initial condition. It's built into the governing equation. The initial conditions would be starting from rest at position 0, y of 0 and y dot of 0 are both 0. Okay, so the simplest initial conditions is what we'll go with because it'll probably make our life a little easier. So let's go ahead and apply those. So, for example, y of 0 equals 0. Okay, y of 0 equals 0. I want to put in a 0 wherever I see a t. Right, so the first term, I'll get c3 times the cosine when I put in 0. That's the cosine of 0. All right, plus I'll get c4 times the sine. When I put in a 0, it'll be the sine of 0. All right, and then finally this guy plus f divided by k minus m omega squared times the sine. When I put in 0, it's the sine of 0. Oh, yeah, thank you. The steady state is cosine. That changes things. Yeah, so I copied that wrong. It's cosine omega t when I added them together, right? Right here. Okay, good. And so this is going to be cosine of 0. All right, so this does require you to understand, what are the sines and cosines of 0. Okay, and so people have asked repeatedly already on the on the final exam, is it going to be cumulative? And I made the point that all the math we cover in here, right, is used again, or we wouldn't be covering it. So are we going to separately test your knowledge of trig? Well, not separately, but you got to have your knowledge of trig in order to do the differential equations, right? So cosine of 0 is how much? 1. Okay, so I'm going to get C3 over here. This is 1. Sine of 0? This is 0. Cosine of 0 back to 1. Okay, so apparently this is all equal to 0. I can solve for C3, right? C3 is equal to what? Yeah, negative this coefficient, right? Minus f divided by k minus m omega squared. Okay, so I do have a value for these C3. Okay, what about C4? How am I going to get C4? I need the next condition, right? Y dot of 0 equals 0. Okay, and so y dot of 0 equals 0. This does not mean take y of 0 and then take the derivative. Okay, that would be the derivative of a number, which would always give you 0. Okay, what it means is go back to the original equation, take the derivative, y dot, then evaluate that at 0. Usually, when you solve these problems, you'll try and do as much of this with as little ink as possible. Okay, here I'm going to make sure that we're clear what's going on. So let's take y dot first. All right, y dot of t would be equal to what? So I got to take the derivative. So the first term, okay, number 1, I already have the C3, right? Okay, so I can put that in. All right, so I'm going to have negative f divided by k minus m omega squared. That was the C3 I already found. And then I have the derivative of the cosine, which gives me what? Negative sign, and this root k over m comes out front, right? So I'll get root k over m out front. The negative comes out front, so I'll make that a positive. Okay, and then I'm going to get a sine function, root k over mt. Okay, and so that's the derivative of the first term. Second term, I got C4. Derivative of the sine is what? So I'm going to have C4. I'll have a cosine. What about this root k over m? Comes out front, right? Root k over m cosine root k over mt. Okay, and so that's this term. And then finally, the last term is a cosine function. All right, and so derivative of cosine is sine. So I'll have f divided by k minus m omega squared out front. All right, and then I'm going to have sine omega t, but the omega comes out, right? So it's going to be minus omega sine omega t. So there's the derivative. Okay, now, what we want to do...
Plus or t.
Say again?
Not right before, after the equal sign, it's a plus. Okay.
Are we good? Yeah, so over here, this started negative. When I took the derivative, I had another negative, so I made it plus. You guys with me? Okay, over here, I think we're good. C4 cosine, and then a sine. Okay, and so that is y dot of t. So to apply the condition, I have to evaluate that at 0. So it's y dot of 0, and I'm going to set that equal to 0. So here's the thing. Rather than rewrite all of this ink, can we see what we're going to get here? What's the first term going to be? It's the sine of 0, right? So first term 0. Second term, what's the cosine of 0? 1. So I'm going to get C4 root k over m, right, times 1. And how about the third term? It's a sine of 0, which is 0. Okay, and so the conclusion here is what? Yeah, C4 equals 0. Okay? So let me just be clear about something so that you understand, evaluating these things in practice. I warned you guys when we started DiffyQs that they tend to be kind of long and tedious. The math isn't difficult. It's not conceptually hard. It's a recipe, but you got to follow the steps. The more efficient you can get at the steps, the less painful solving these kind of equations will be for you. Okay, and so for example, when I look at this equation here, and I know that I need to apply a condition on y dot, can't I look at this and immediately say, when I take the derivative, this is a sine, this is a cosine, and this is a sine? And as soon as I know that, I can go immediately from this step to this line right here in my head. I don't need to write this whole thing out to conclude this. Are you guys with me? Right, if I realize term by term, this derivative is a sine, evaluate at 0, that gives me this 0. I look at the middle term, this is a cosine with a root k over m that comes out, evaluate at 0 gives me 1, I can write this down. And then the third term over here, this will become a sine, I'll evaluate at 0, it'll give me 0. Okay, and so the point is, you can be efficient as you work through these initial conditions, but it provided this complete derivative in the middle just to make it really clear what we're actually doing. Okay, you do have to take the derivative and then evaluate it at 0. How much writing you have to actually do to accomplish that is up to you. Okay, and so just want to make it clear, if you want to solve these in an efficient way, as long as we're clear that it can be done in your head from one line to the next, that is fine. Okay. Questions on how we solve for the initial conditions? Okay, because in a lot of these kind of problems, trying to get all the way to the end and have an answer, it's like the devil's in the details. Right? So you can get the idea, but ultimately you can either execute this and solve an equation or not. Right? And on the exam, we got a grade if you can actually do this. You guys with me? All right, so I've got the constants now, right? I got C4, I got C3. So now, when I finally look at the answer, the total solution is this guy, right? Except the C4 is the kind of answer we like, 0. So the final answer is not as messy as the general solution in between. So finally, final result is y of t is going to be C3 cosine root k over mt. There's C3 minus f divided by k minus m omega squared. That's C3 cosine root k over mt. Right? The C4 is 0 plus 0, and then I have this term, which is again the same thing, f divided by k minus m omega squared. But now it's a different frequency. It's the cosine of omega t. Can I do anything to simplify this algebra? Yeah, I mean, I've got the same constant in front, right? And then this is a negative and this is a positive, so I could kind of flip the order of those two, right, and write it as a subtraction. So the most elegant way to write this, I think, would be factor out this amplitude-looking function here, right, f divided by k minus m omega squared, and multiply that by this one minus that, cosine omega t minus the cosine root k over m t. And this is what would have a box around it as the final solution that satisfies the governing equation and satisfies the initial conditions. So, how do you know if this is right or not? Okay, that's one thing. I can apply the initial condition. So y of 0, when I put 0 in for time, 1 minus 1 is 0. Done. Y dot of 0. Yeah, this is going to be a sine. This is going to be a sine at 0 minus 0. It's done. Initial conditions are satisfied. I know that's true. The other step would be this. Okay, this is messier to show, but if I want to know if my answer is right, this is just like solving a quadratic equation. I get two answers for x, plug them in, see if you get 0. If I take this and I take its second derivative, I could plug the second derivative here. I could plug everything in this box here. And if I combine all the algebra, when I'm done, I should get f cosine omega t. Okay, so you can go back and check that. It's another half page of algebra to do, but you can always check and make sure your solution is correct. which is a satisfying kind of thing. Right? It's one reason we like closed form solutions. Okay, exact answers. All right, so question is, what piece of physics can we get out of this? Because we solve all these problems because we want to understand some information. And in fact, during the process, right, I recapped even at the beginning, if I just displace this guy and let it go, then it oscillates at a frequency root k over m. Okay, that is the natural frequency. And then I can come in and I can force it at some other frequency, right, faster or slower than what it was. Okay, and I'll have an overall response of the system that looks like that. Okay, but this solution is only good if omega is not exactly equal to, right, in other words, the forcing frequency omega is not exactly equal to this number. Okay, so this kind of begs the question of what happens then, right? So what happens as omega, it can't be exactly equal to it. If it was exactly equal, then during that solution process, I'd have a divide by 0, right? Right here, I'd have a divide by 0. I got a problem. But what if I approach that number? Okay, kind of like a limit. We talked about the limits with derivatives and again with integrals. I can get close to that number, right? I can get 90% of root k over m, 99%, 99.9%. As long as I'm not exactly it, right? I still have the answer. So take a look at the math here. What happens to y of t? Well, I still got an f here. What about the denominator? As omega approaches root k over m, this denominator approaches what? 0, right? I square it, I get k over m, the m cancels, k minus k gives me 0. Well, the front looks like that, which is a problem. Okay, note that this is not an equal sign, this is approaches. Okay, so I get something here that's going to look like a big number, right? Denominator approaches 0, this starts looking like a big number. So one thing immediately would be like, well, that's a problem, the solution starts to blow up. But it gets a little more complicated because what happens here? When this number approaches root k over m, how does this term compare to that term? They become the same, right? So everything in the parentheses looks like 0. So I'm trying to understand the physics of what goes on here, right? And so, what happens is I get a number divided by 0 multiplied by 0. A number that gets really big multiplied by a number that gets really small doesn't tell me a whole lot. Okay? In fact, if you've had some calculus, there's methods to analyze this stuff further. This is called an indeterminate form. Okay, and so it's a 0 divided by 0, indeterminate. Okay, the answer, by the way, of 0 divided by 0, if 0 was an exact number, right, anything divided by itself is what? 1. Okay, so you might think, hey, maybe it's 1. Okay, but if the denominator approaches 0 faster than the numerator approaches 0, then the answer won't be 1, it'll be what? Infinity. Okay, and if the answer, okay, for the numerator approaches 0 faster than the denominator approaches 0, then the answer is 0. Okay, and is it approaching it from the right or from the left, right? In other words, is this a positive or negative number? Depends, right? And so here's the bottom line. Your answer is somewhere in between negative infinity and positive infinity. Okay, and that's what you can conclude from that analysis. All right, so there are methods of calculus where you can do some limit operations and do some more things with derivatives to get this understood better. Okay, that being said, if I'm an engineer and I really want to know what happens when omega approaches root k over m, can't I just stick this equation in MATLAB, okay, and plug some numbers in here and plot it, right? And examine what actually happens. So we can do this limiting procedure, whether or not we've had calculus and we've looked at these other methods, I can analyze the behavior. So let's take a look at that. Okay, and we'll fire up a little bit of MATLAB here and see what it might tell us.
What are we doing to get word? Before this is over, can you tell us when those review sessions are?
Yeah, I will send out an email on review sessions.
Because I want to go to one of those things.
Last night, I was so lazy that I did Alex EGR. You carried me down from the second floor.
All right, so here's what I did.
And I let him use the elevator.
All right, so the question is, what happens when omega approaches root k over m? All right, so physically what we're saying is, I got an answer that is correct, right, as long as I don't force it at exactly the same frequency that it would vibrate on its own, right, by just displacing it and letting it go. Okay, any other frequency, the answer is exactly that. And the question is, well, what about when it's really close to that? Okay, and so the way you can look at this is you can just write a MATLAB code. I got this one here, okay, where you can examine that exact equation for the answer. Okay, and so we'll do that here. Let's see. See if I can run this. Okay, so this is up on the page, so you can run this thing yourself. What I did was just coded up the answer. This is it right here. F divided by k minus m omega squared times cosine omega t minus the cosine of square root k over mt. Okay, so this is the answer. What I'm going to do is plot this thing for 3 values of omega. Okay, so first thing, set all the parameters equal to 1. F is 1, m is 1, k is 1. So we got numbers in. And then we'll take omega compared to root k over m. Well, if root k over m, if everything's 1, then root k over m is 1. So this one would be omega is 90% of the way. Okay, so it's not equal, it's 90%. This one is now I'm 99% of the way. And then this one I'm 99.99% of the way. Okay, and can we take a look at what the solution looks like, y as a function of time, over time for these different forcing frequencies? Okay, so that's all that is. So let's run this and see what it does. Got to give it a name. All right, so what I've got here, here's the command window. I got to pause on there so we can see what it's doing. Put it down here a little bit. Okay, and so right here, I just define a vector for t, right? So we're going to go out 200 seconds in time. We're going to define omega to be 0.9, and then here's the equation with omega is now 0.9. Every other parameter is 1. Okay, and now we're going to plot that result. Okay, and you get this guy. All right, it looks like that. Okay, and so this is really an odd kind of behavior. This is time here. This phenomenon is called beating. Okay, and what it looks like is almost like a breathing type phenomenon, right? So it's like an oscillation trapped inside another oscillation, okay? But that, this is the behavior in time. So the amplitude ramps up and then it ramps back down. And it ramps up and then it ramps back down. Okay, anybody here drive a beater car? It's a room full of college students. Come on. Yeah? Yeah, so people drive beater cars, right? Do you ever have one of these cars where you approach 57 miles an hour and all of a sudden the steering wheel starts to shake, right? Does that happen to you? Okay, so what do you do, by the way, to fix that?
Go faster.
Yeah, most people speed up probably, right? But slow down is one. In fact, it works either way. Right? If I speed up or I slow down, I'm okay. If you sit there right at the 57, right, what probably is going to happen is something like this. It'll start to shake a lot, then it'll slow down a little bit, then it'll, it's not slow down's the wrong term. It's the amplitude we're talking about. It'll shake a lot, then it'll shake a little bit less, right? And a lot. And in fact, you can experience this acoustically too. If you're a musician, you can get around and you can start trying to apply excitation to a string instrument in a way where you're doing it close to the frequency, and you can observe this in an audio kind of way. Okay, so kind of cool. So now what happens, but I'm not really there, right? I'm only 90%. You get this kind of behavior when you're a significant percentage of the natural frequency, but not completely there. Okay. By the way, if I'm flying an airplane and the wing is doing this, is this good? No. Probably not. Okay. Let me show you what's worse. Okay. What's worse is if I get 99% of the way. Okay. Down here, omega now is 0.99. Okay. And so if I'm now 99% of the way there, okay, then here's what the solution looks like. You know, mind you, this is the same exact equation, right? I didn't change the equation. I just changed the value of the parameter, omega. The function of time, it's the same thing. It's cosine omega t minus cosine root k over mt. It's just the omega now is very, very close to the k over m.
Can I see what happens when it's 999?
Yeah, absolutely. So, and this is an interesting result, right? Because on 90%, I get this kind of weird fluctuation, right? Now, how would you describe this? If you had to describe this in words, this is time. This is the actual displacement. Yeah, it's a steadily increasing amplitude over time. Okay, this is like a sine function trapped between what? Two lines, right? It's a sine function trapped between two lines. It's a solution that looks like a t times a sine, right, is essentially what's going on. Okay, and so that's what you get, but look how big the amplitude gets, right? The amplitude, instead of this number, these numbers are like 10, this number's 100, right? This thing ramps up. Okay, and then what happens, the request was, what happens when I hit 99% of the time? Okay, and we can get that, right? Here it is, 99.99. Okay, and so we'll hit return again, see what we get. We get this guy.
It doesn't really look that much different.
Correct. Okay, so here's the thing. The question is, from an engineering standpoint, when is omega equal to root k over m? Well, my solution's no good if it's exactly equal. But it's good if it's equal to 4 significant digits, to 5 significant digits, to 15 significant digits. None of those are exactly the same number, right? And so there's nothing wrong with it mathematically, and you can see what literally happens. The point is, I'm already at the limit here. 99% of the way is as good as 99.99% of the way. Teeny bit increase in amplitude, right, out here. But essentially what happens is this is called resonance. Okay, and so if you are really, really close to the frequency, by the way, in your car, that's usually related to rotating unbalance of the tires, right? And so you got a rotating unbalance there, and the speed is the frequency that you're spinning the tire, right? And so if the tire wants to bounce around at a certain frequency based on its imbalance, right, the speed of the tire is forcing it to want to vibrate the way that it would want to vibrate on its own. So if you speed up, you change the frequency, and all of a sudden my beater car drives nicer at 65 than it does at 55, okay? Or if you slow down, 45 instead of 55. But this is it. Okay, and so in mechanical design of structures that move, okay, which is most mechanical things, not all, you really got to worry about vibration. Okay, there's been a lot of cases in history that have motivated modern vibration research, and it's because, you know, things like in civil engineering, if you build an entire bridge like they did with the Tacoma Narrows Bridge, okay, and you don't consider what happens under dynamic loads, then you can have a bridge that when the wind blows just right, okay, that bridge has a tendency to vibrate in that plane at a certain frequency, and if the wind blows it at that frequency, the bridge starts to do this, okay? And if a bridge starts to do, frankly, either one of these things, this or this, what you end up with is structural failure, all right? And so stuff breaks, bridge falls down. If this happens on an airplane, you could, you know, potentially snap the wing off kind of thing. Okay, so this is also why, you know, all real objects, right, this is a spring mass system, right, and this is what we call 1 degree of freedom. It vibrates up and down, it has one frequency, okay? But when I hit something, and you guys hear that noise, this desk, right, every real object, everything you can ding, that doesn't ding. Okay, so, right, I need a piece of metal. Anything you can, there you go, that's better. There you go, right? Okay, when you hit that, you know, real objects continuous objects, they have an infinite number of vibration frequencies. That can vibrates in and out, it vibrates up and down, it vibrates in this way, it's got all these different modes of vibration. They all have different frequencies. So in engineering design, if I'm designing an aircraft engine that's got a bunch of disks that all spin just like your tire spins, I'm going to hit natural frequencies of the wing, of the rest of the engine, of the overall aircraft. And the key thing is, just because I hit that frequency doesn't mean it's going to break. What it means is, I better not sit it there, right? It takes time for the amplitude to build. Okay, even this, it takes time for this to build. So in design, what you basically say is, I got to know what the frequencies are, and if I got to ramp up, I better get through the resonances in a hurry. I don't want to sit and operate something at its resonance. Okay, so that's the lesson on vibration design. You got to worry about things because otherwise you get this and stuff breaks. It's not good. Questions? Yes?
So how did people that build bridges prevent that from happening?
Yeah, that's a great question because really modern day analysis understands this stuff pretty well. Closed form solutions for things like springs and masses and the kind of stuff we're doing here have been around a long time. So they would have known that, and in fact, I believe the case I cited, the Tacoma Narrows Bridge, I think they did do structural vibration analysis in the design, but they didn't consider all the modes of vibration. So they considered things like, you know, cars are going across and it's going to vibrate up and down, but they didn't worry about the side to side, right? Or the twisting of the bridge. Like any way that you could envision something oscillating or moving needs to be considered. Okay, nowadays, we've got computer models of everything. Complete three-dimensional structural models of everything. Cars, bridges, these things. So we can actually do vibration analyses that will identify all these different possible modes. Okay, so new structures, buildings, and all the rest of that, they can do very good analysis. And buildings now built to like earthquake standards and things like that take into account the types of dynamic loads you could get with a, you know, with vibration. Okay? So, but bottom line is you learn this stuff over time. And then when you design something new, right, that's the other thing about all the computer models. I can make solid models. I can design whatever I want for a piece of equipment, right? For a car or a motorcycle, I can make changes just for the aesthetics of it. It's going to look cooler now. It's going to be more aerodynamic or whatever. When you change the geometry and the material, you change the vibration characteristics, right? And so all of these types of analysis got to be done every time you do a design for something dynamic. Good? All right, that is differential equations in mechanical systems. The notes have one that's near and dear to my heart. In fact, Josh threw this one in here. It's actually Newton's law of cooling for a cup of hot coffee. Okay, and so that's in the notes. I really feel like we need to do justice to the electrical applications because there's some really good applications there. So that is actually the topic for this week. So we'll get started with the last set of lecture notes, which is differential equations in electrical systems today. We'll get as far as we can through the first example of a low-pass filter, and then the last day of class is Thursday, and we will wrap up with the second-order LC circuit as well on Thursday. Okay. While I was putting this up, we had the question about review sessions. Those have been identified. Angie has sent me an email, so all I've got to do is post it and send it out. So we do know what the review sessions are, okay? And I don't know what they are. They're in my email. Okay, so look for an email later today. We will have 3 review sessions. The exam is next Thursday, 1 week from Thursday, noon to 2 o'clock p.m.
For me, that's the last thing I have to do for all of my classes.
Well, and that's the goal. In fact, we figured a number of first-year students, if we put this exam in the unscheduled block on Thursday, I mean, one reason is so we won't have conflicts and don't have to deal with makeups for the final, but you know, separately it was because this really gives you guys an opportunity to say, this is the performance I need to get the grade that I want in the most important class for my engineering career, okay, which is this class. Okay, and so you make a decision what you're going to try and do between now and next Thursday. You got 9 days. In a college student's life, that's like an eternity. Okay, so you can master whatever needs to be mastered and try and post the grade that you need. Okay, again, the most dramatic case I've ever seen of this is somebody that posted grades, low C grades, low 70s grades on both midterms 1 and 2, and had a perfect score in the final.
That's a lot.
Yep, I'm just saying it can be done. So no matter what your prior performance was, you got a chance here.
Luckily for me, that'll be the last class I'm focusing on Wednesday.
And that's the goal. Okay. So, differential equations in electrical systems. The first one, really very interesting application called a low-pass filter. Okay, so this is differential equations. In electrical systems. Okay, and we will do an example of both a first and a second order. Okay, and so the first example is what we call a low-pass filter. Okay, and again, the idea is that in electronics, because we know that things like inductors and capacitors have derivative relationships, right? V equals, or I equals C dV dt, right? And an inductor, V equals L di dt, right? So we have these input-output relationships. We can control rates of change of current and voltage by putting circuit elements in the circuit. When we combine them all together, it enables us to control signals that go through circuits. Okay, so any kind of electronics device is designed essentially to transmit electrical signals, right? And sometimes it's really an obvious application like an audio application, right? So I can put filters in an audio application to get a low signal-to-noise ratio, right? And try and keep the noise down, get clear sound, those kind of things. In an electric circuit in general, I can think the same way about output voltage, output current compared to the input, trying to get the noise out of the system. When I want to get noise out, whether it's low frequency noise, high frequency noise, I want to put filters electronically in the circuit. Okay, and this is an example. So it turns out that all you need to do this is a resistor and a capacitor. Okay, so I can have over here, plus or minus, I can have a voltage source. I'm going to call this Vs of t. That's my source voltage. Okay, and if I hook it up to a resistor, and then I hook it up over here to a capacitor, okay, then what I will have in the circuit, okay, is plus or minus an output voltage V of t across the capacitor, okay, and this is the capacitance C, this is the resistance R, okay, and so here's the way to think about this. Number of different ways you can do the analysis. You can think about it in terms of Kirchhoff's voltage law. Let me look at it a different way, the way we have it here in the notes. If you think about measuring this output voltage across two open terminals, okay, one way to do the circuit analysis is to say that essentially I've got three currents here. I've got I1, the current going through the resistor, and then I reach this intersection. Okay, and so the current can take a corner this way, right, and that would be I2. Or the current can go straight, and that would be I3. Okay, now, maybe this is an overly complicated way to think about it, because if this is an open terminal here connected to nothing, what do you think the I3 is? 0. Yeah, so the I3 is really 0, which means the I2 is the same as I1. Okay, so again, do I need I1, I2, I3? Well, I'll show you why. Here's the argument. You know, this is like volume flow. Current is actual flow of electrons, right? So conservation of mass applies here. So whatever I1 is, if it hits an intersection, it has to be equal to the sum of the other two, right? So I can say I1 is I2 plus I3. That's a true statement. And then I can begin to identify what each of these currents is based on my governing laws. So for example, across a resistor, I get a voltage drop V equals IR. Well, the V in the V equals IR is the voltage drop between the 2 points on either side. And on the left side, the voltage I have is Vs. And on the right side, the voltage I have is the difference between these 2 points, which is V. Okay, and so I know what the voltage drop across the resistor is. So V equals IR means that the I1 is the voltage drop divided by R. So it's Vs of t minus the output V of t all over R. Okay, that's what I1 has to be. Again, this is V equals I multiplied by R. And then finally, the I2, we know from our derivative relationship, right, is equal to C times dV dt. That's the way that capacitors work. Okay? So that's it, right? And I know what the values are here. I got I1, I2, I3 is equal to 0. I should be able to plug that all right here. All right? And so I1, right, is equal to I2 plus I3. Let's just plug the numbers. Vs minus V, Vs of t minus V of t, all over R. That's going to be I1. That's equal to I2, which is C dV dt, plus I3, which we said had to be 0. Okay. And that's it. Okay. And so Vs of t is my source voltage. V of t is the output that I'm trying to measure. Okay. And it looks like I have an equation here that's got V of t, and it also has the derivative dV dt. Okay. And so what I've got is a first order differential equation. All right, so the way I can arrange this, if I multiply all through by R, right, then I'll have Vs of t minus V of t is equal to R times C times dV dt. Okay, and if I put everything with V in a derivative on the left and everything else on the right, then I really need to flip this around and write it as RC dV dt plus V of t is equal to the source Vs of t. So let's suppose that I apply a source that is sinusoidal. So let's suppose that source is an alternating current, alternating voltage in this case, right? Vs of t, and what I'm going to use for this one, we used a cosine for the vibration of the spring mass. Let's use a sine, E times the sine omega t. Okay, so capital E is the amplitude of the source voltage. Okay, and let's also assume, if this is a first order equation, okay, that my initial condition is I have no voltage across the capacitor. Okay. So if all of that is true, okay, then let me go ahead and write as the problem statement here the resulting differential equation. It'll be this guy, right, with Vs being that and the initial condition there. So what we'll have is Rc times dV dt, I'm going to write that as V dot of t, plus the voltage V of t is equal to the source, which is E times the sine omega t. Okay, and then I'll put my initial condition, which I need only one, V of 0 equals 0. Okay, and so this is the problem that I would like to solve right here. Okay, I'll put a box around it so we're clear. So again, reiterating, right, whenever I can in this class kind of talk about the origin of the math, I do it because, you know, it's fun for me, right, and hopefully it's motivating. Okay, but again, your responsibility on the final exam is to be able to solve a differential equation in whatever context we give you. So we're not going to be asking you to derive the differential equation based on the circuit knowledge, right? That's the kind of thing you might do later in circuits. But here, you'll have a picture and you'll have an equation with a governing equation, initial condition, and you'll be asked to solve it. Okay? So what we have right here on the left will be the starting point for, again, all the homework and for your final exam. And so what we'd like to do is apply the recipe and see if we can understand why is this thing even called a low pass filter and exactly how does it work. Okay, that's the goal of solving this equation. Questions on that? All right, very good. So back to the recipe, and as I warned when we started this, it gets a little redundant, right? Every single one of these problems is solved exactly the same way. Okay, which also means we ought to be able to pick up the clip a little bit, okay, the pace at which we solve this guy. Okay, but again, I'm not just going to blow through it on my own. All right, so I want you guys to prod me along here. So step number 1. What do I do? Set the input equal to 0 because I'm finding the transient solution, right? So transient solution, and I'll say what you just said. Let's set the right-hand side equal to 0, okay, which is the input function. So great. no input. What I have now is RC times V dot, that's the derivative, right, plus V of t, and that's now equal to 0. Excellent. Next step. All right, so what we're going to assume is e to the st, right? So V tangent of t is equal to e to the st. The reason we assume that is so that when I take a derivative and add it to itself, I'll have an e to the st in each term, right? I can add up like terms and get 0. So let's go ahead and plug it in. RC, the derivative of e to the st is what? S e to the st, right? Plus I've got v of t, which is e to the st, and that equals 0. What can I always do at this point in the equation? Factor out an e to the st. If I cannot factor out an e to the st, then I did something wrong when I subbed it in, right? Because that's the entire point of this procedure, is to have like terms, okay? And so what I'm left now with is RC multiplied by S plus 1, okay? And that equals 0. What am I trying to solve for here? S, right? I want to know what is the S value that'll make this work. That's the process in step 1. Okay, and so what about this? E to the st, is that ever 0? No, this is never 0. And so the conclusion has to be, right, that RC times S plus 1 equals 0. Okay, and that means that S is what? Yeah, it's minus 1 divided by RC. Okay. So once I have the S value, then how can I write the transient solution, V tangent of t? Plug in the S, okay? So this is S. How many S's do I have? 1. So you can call this S1. If it was second order, I would have how many S's? 2. First order, only 1 S. So always, I plug it in, but remember, there'll be a constant, right? C1 e to the S1t. The reason there's a constant is the right-hand side 0. Any constant multiple will get factored through and canceled out, right? So it's a general solution if I put the C1. Okay, and so let's go ahead and plug the number in. V tangent of t is equal to C1, some unknown constant, e to the minus 1 over RC, okay, times time. By the way, no matter what the C1 is, how would you describe that physically? What's going to happen there? It's a decaying exponential. Okay, there's a pattern to these differential equations, right? The transient solution is always exponential. If it's an imaginary number, an imaginary exponential is really sines and cosines. It oscillates. If it's not an imaginary number, like this, 1 over RC, okay, then it means it's a decaying exponential, which means as time gets large, what's this equal to? 0, which is why we call it the transient solution. Okay? How fast does this thing go to 0? What does that depend on? Does it depend on this guy? Does this say how fast it goes to 0? This is like, actually, what is this? The C1 is what? So if this was a sinusoid, you'd call it the amplitude, but can you be more specific on an exponential? Let me ask you a leading question. What's the value at t equals 0? C1. C1. Okay, C1 is the starting point. So it doesn't say how fast it decays, it says where it starts. So I start here, and then as t gets big, I go to 0. How fast do I go? Multiples of what? Multiples of t. Multiples of r times c, right? When t equals rc, this is e to the minus 1. When t equals 2rc, it's e to the minus 2. When t equals 3rc, it's e to the minus 3. rc is the time constant here. Right? So does this happen fast or slow? Think about the numbers. right? Typical numbers in your lab. I got a resistor, which is whatever, a couple of ohms. I got a capacitor, which is what? Microfarads. E to the minus 6 times a couple of ohms is still e to the minus 6. If it's times 3 or 400 ohms, it's e to the minus 3. These things decay electric circuits on the order of milliseconds, right? Very quickly, the transient stuff's gone. Okay, but it's part of the answer because it initially it affects the total solution. Okay, and so the stuff that happens right away when I flip a switch, when I start something up, the right away stuff, right? You see this in laptops and things all the time, right? And when you turn things off, it's the same reason. If something's not working and you shut it down, you probably ought to wait a little bit, right? Because stuff's happening while it's technically off. Okay, if you plug it back in, it changes what goes on. Okay, and so, yeah, so that's a transient, it goes away. Great. Next part. By the way, this right here, transient solution, that's 5 points on the final exam. Okay, we'll break this down in part. 5 points right there. Next part. Steady state solution. Okay, so how do I find a steady state solution for a problem like this? What kind of steady state solution, right, is gonna satisfy this? Yeah, so keep in mind, as soon as you move to steady state, that's what the math department, the differential equations book will call the particular solution. It is the particular one that works for this input. That's what that language means. Okay, the one that works for that input. So remind yourself, you're going back to the original, not the one with 0. So write the original equation back out, right? So you're clear that this is what you're working with, right? And on the right side, I got E times the sine omega t. This right side is my forcing function. In the recipe, this is the f of t, right? So what I'm doing is I'm saying what kind of function, when I take its derivative, multiply by a constant, add it to itself, can still give me a sinusoid? The answer is not going to be a polynomial, right? The answer is not going to be, an exponential function. Could be a complex exponential, okay, with j's, right? But it won't be decaying exponential. So the point is, it's an engineering approach. Use something that might work. What might work is other sines and cosines. Not any sines and cosines, ones that have the same frequency, right? I can't add sine of 2t to the sine of 3t. They don't line up, okay? So I got to have omega if I'm going to add these up and get like terms. Okay, so same idea. I have to assume it's the same. So let's assume, okay, that v steady state of t. Okay, and again, when you solve these differential equations, be really anal with your notation. V steady state, there's 2 s's. I already have a v with 1 s over here, okay, which was this guy here. All right, be careful not to duplicate notation and get confused. So what am I going to use? Sines and cosines, I'll use a times the sine omega t plus b times the cosine omega t. Right? Any combination of sines and cosines could work. So if I'm going to use this, what am I trying to solve for here? I want the a and b. How am I going to get the a and b? Right, I need the a and b that will make this equation true. So I should do what with this? Plug it in here and see what I can figure out. So I'm going to need the derivative, right? When I plug this in, I'll need the derivative. So let's go ahead and do that. V dot steady state would be what? Derivative of sine is cosine. The omega does what? A omega cosine omega t. Next term, derivative of cosine, negative sine. Omega comes out, so it's minus b omega sine omega t, right? So that's the v dot steady state. Okay, and so what I need to do is plug this all into the equation. So it's RC multiplied by v dot. So that's a omega cosine omega t minus b omega sine omega t. Okay, that's the RC times v dot. then I want to add the v. Well, the v is a times sine omega t plus b times cosine omega t. All right, so that's now the entire left-hand side. Make that b a little better. All right, so this is RC v dot plus v itself, this entire term here. Okay, and that has to equal the right-hand side, e times the sine omega t. So I'm back to the situation again where I have one equation and I'm trying to solve for how many unknowns? 2, a and b. But at this point in the course, this becomes very familiar to me because I already did this with vectors where I had one equation, but I had i's and j's, so I turned it into 2. And then when we did sinusoids, right, where I was trying to write the sum of two sinusoids as one sinusoid with a magnitude and phase, and I had equations that looked just like this. I had sines and I had cosines on both sides of the equation. And what you do when you have that is what?
Take the coefficient, like, yeah, sine omega t, sine omega t, so you take the average.
Right, so I need to group the sines and group the cosines, and then I need to compare the coefficients on both sides of the equation, right? It's the same strategy that we've already used in here. Okay, and so great, let's do that. Let's line up the sines and let's line up the cosines. So if I line up the cosines first, and at this point again, the more efficient with the algebra that you can be, the happier your hand will be when you're doing the writing, okay? Because it's a lot of writing. So look, here's a cosine omega t here. Here's a cosine omega t there. I don't see any other ones. Looks like I can do this together, right? So multiplied by cosine omega t, won't I have RC omega times A? That's this one. And then won't I also have B? So plus B. Those are both multiplied by cosine omega t. I can double check to make sure I have all the cosines. Cosine omega t times RC omega A. That's the first term. Cosine omega t times B. That's this term. There's no other cosines left, so I got the cosines. All right, now let's do the sines. What would multiply by the sine omega t on the left side of the equation? Yeah, I've got an A right here. I got RC omega B, which is negative. So I might want to write this as A minus RC omega B times the sine omega t. So again, check the terms. Here's the sine omega t, RC omega b negative. RC omega b negative sine omega t. All right, and then here's the A sine omega t. I got that one there. And then finally, on the right-hand side, I've got E times the sine omega t. So all I've done is one line to rearrange the algebra. So I have something times cosine, something times sine, and then I have the right-hand side. So it's still one equation, but now how do I turn it into 2? Do what? A and B are both unknown currently, right? We're trying to find what is the A and the B that make this the solution that works for this equation. Okay, so I still have one equation, but I would argue that we're already at the point that I can write it now down as 2. And I do that how? I compare the coefficients. Something times cosine on the left. What's multiplied by cosine on the right?
0.
Nothing. Okay, so if I look at the cosines, all right, that's the first set of coefficients. Then whatever's on the left better be 0. RC omega A, okay, plus B has to be 0. Okay, so right away, right, I ought to be able to solve for either A or B in terms of the other one, right? And so I'll solve for B. This means that B has to be negative RC omega times A. So that's one thing. Okay, call that equation 1. Okay, and then if I look at the sines, whatever's in front of the sine on the left has to be the same as whatever's in front of the sign on the right. So don't I get A minus RC omega times B, right? And that would have to be the same as the coefficient on the right, which is E. So that's equation 2. Now, both of these have two unknowns, right? We can go back to, two equations, two unknowns. We could use the matrix method, right? Or I could do what? Yeah, brute force substitution at this point makes sense to me. And so, look, this is already B in terms of A. Can I just plug 1 into 2? Plug 1 into 2 and see what you get. All right, and so if we do that, it's going to be A minus RC omega times B. Well, B is minus RC omega times A, right? Just plug it in for the B right here. This is equation 1. That equals E. And then again, you got to be a little comfortable with your algebra. What can I factor out of these two terms? The A, right? This is all one term. This is multiplied. There's two terms. So I've got A times 1. This is negative, negative, which is the same as positive. RC omega multiplied by itself is what? RC omega, quantity squared. Right? That's what's on the left. Okay? And that's equal to E on the right. So I'm getting close here. So then apparently A is what? Yeah, A is E divided by the parentheses. 1 plus quantity RC omega squared. All right, that is A. And here's the beauty of the substitution method. Once you get the 1, the other one's already in terms of the 1. So I don't have to do much. Immediately, I can write right next to this. B is this same thing with now a numerator of RC omega. Right? So it's going to be minus RC omega E divided by the same denominator, 1 plus RC omega squared. So here's the thing. Interesting thing to note. When we did the second order problem and we did the steady state solution, it was sines and cosines also. Right? This was last class, you might not remember. One of the coefficients turned out to be 0, which makes life nicer. Here, the equation seems like it's probably simpler. It's just a first order. Okay, a lot of times the first orders with forcing functions are messier algebraically. This is a perfect example, right? I've got non-zero A and B. So my steady state solution has two non-zero terms in it. Okay? Again, it's the reason why math profs always complain about students in math classes. They say, well, they're not ready for calculus because their algebra is bad. It's two different issues. Right? If your algebra is bad, your algebra is bad, and you need to fix your algebra. Okay? It doesn't actually mean you're not ready for calculus. There's people in this classroom right now with bad algebra. Right? I don't know if anybody wants to admit it. All right, but if you've got bad algebra, okay, but you can still understand calculus. We've been doing calculus for 6 weeks now or something, right? And we can understand it. So just keep practicing the algebra because it's true. The algebra pops out all over the place, and you got to get comfortable moving letters and numbers around equations. Okay? So let's see. I got A and B, so we'll come back to here, right? Transient solution. Maybe put a box so we don't forget what that was. Okay, and let's go ahead and write out now that steady state. What does that look like? So, V steady state is going to be what? I got an A and a B, both non-zero. So it's A sine omega t, that's E divided by 1 plus RC omega squared, okay, times the sine omega t, plus I got B times the cosine. B is negative RC omega times E divided by 1 plus RC omega squared, right, times now cosine omega t. Can I factor anything out of that to make life a little easier? Yeah, this whole coefficient here, E divided by 1 plus RC omega squared, I can factor that out kind of like an amplitude. Talk more about that in a second. Times sine omega t, right? And then over here, what would I have? The E is already out, right? So I would still have the negative and the RC omega, and I'd have the cosine omega t here. Okay, so this is one way to write the steady state solution, okay, which is okay. But here's the thing. If I asked you, number one, describe this function for me, what does this do? I mean, you could pull out MATLAB or your calculator and code this in and plot it and look at it, but at this point, right, we should know enough about sines and cosines. What's this function going to do? It's just going to oscillate. It's a sine and a cosine. Is it the same or different frequencies? It's the same frequency. So it's, you know, this steady state solution by itself, not like the spring mass we just talked about, where one was root k over m, the other one was omega, two different frequencies. I can't combine it in any way, and it does weird stuff depending upon the value of omega. This doesn't do weird stuff. It's omega here, it's omega there. It's a sinusoid, sine or cosine with what? I can take any two sines and cosines of the same frequency, right? And I can write them as one sine or cosine with a magnitude and a what? Exam number 2. A phase shift, right? A phase shift. Okay, so the point is, at this point, I couldn't even plot this by hand. And frankly, if I asked you, what's the maximum value of the voltage? Is it obvious? It's not this number, right? Because I got an amplitude in front of a cosine different than the sine. Right? So that whole business of addition of sinusoids, to really understand this, I probably have to do that here, right, in order to see what's going on. Okay, and so I'm not going to go through that entire exercise. Let's look at this at this point more like an identity. Recall that if I have capital A times the sine omega t plus capital B times the cosine omega t, which is what I said my steady state solution was, and I know the A and the B, right? Isn't this the same as the square root of A squared plus B squared, that's the magnitude, times the sine omega t, right, plus a phase shift, plus phi, right? That is essentially a trig identity. Okay, and in this case, right, the way we did that is the whole business that we tested you guys on in exam number 2, right, is this is all based on the idea of, like, you know, the unit circle, and I can have any values of A and B. Here's A and here's B, and this would be phi, right, and this would be the square root of A squared plus B squared. That hypotenuse is what we had called M, right, that's the magnitude. So this is a true statement here. Okay, and so do I know what the A and the B are, you know, in general here for my total solution? Sure. Okay, although my A and B as drawn here are both kind of big messy numbers with a bunch of letters in them. Okay, and so a cleaner way to think about this, okay, would really be, you know, what if I redefine the A and the B, okay? You know, what if this is the A? In other words, 1. Okay, and what if this over here is the B that I interpret here? So I'll leave this in the front, and we'll say, can I take this addition of sinusoids with A equal 1 and B equal to this, and write it as one thing with a phase shift, right? And I ought to be able to do that, right? By the way, what's the phi? Right? Phi, wouldn't it be A tan 2 of B divided by A? All right, so if I know the A's and the B's here, I ought to be good to go. So, what will I have? So this means that what's in the parentheses right here, okay, let me go ahead and write this. This means that the sine omega t, right, plus the minus RC omega cosine omega t is equal to the square root of A squared plus B squared. A is 1, B is this guy. So it's the square root of 1 plus RC omega squared. That's a squared plus b squared. All right, and then that's multiplied by the sine of omega t plus phi. All right, where I know what the phi is. Phi is equal to a tan 2, right, of what? B over a minus RC omega divided by 1. All right, that's the phi. So if that's true, then everything in the parentheses right here, okay, to make it clear, this left-hand side is just this parentheses. We ought to be able to replace it with that, okay, and make life a little easier to understand. V steady state of time is equal to E divided by 1 plus RC omega squared. Right? And now we're going to multiply that by what's in the parentheses, which I have now combined into a single sinusoid. Right? So it's the square root 1 plus RC omega squared, right, times the sine omega t plus phi. And here's the neat thing about this. Can I simplify this even further? Okay, one thing I want to remind you of again. This is a problem in differential equations. We took a couple of derivatives right towards the beginning of the problem. Everything else we've done is algebra, right? And trigonometry. That's all we're doing here. So going from this line to this line, can I simplify this? Yes. Help me out. Who's good at algebra?
I am good at algebra.
All right. I love it. Confidence. All right. So what can I simplify here?
Well, the 1 plus RCW squared.
Omega.
Omega.
Yeah. Uh-huh.
I'm pretty sure there's a way you can simplify that.
Okay. So this whole denominator here looks like what's under the square root, right?
It does.
So what can I do with that? Yeah, I mean, look, it's a square root divided by this. This is just exponents, rules of exponents, right?
Yep.
This is the quantity to the half power. This is the quantity to the first power. Subtract the exponents, you get the negative 1/2, which is the same thing as what she said. Can't you just put the square root in the denominator?
Yeah.
And the answer is yes, right? So don't I really just have E divided by the square root, 1 plus RC omega squared, right, times the sine omega t plus phi. Like that. Bam. Okay, that's the steady state. Worth 5 more points on your final exam. That's a well-earned 5 points. Okay, so this is where we are. We got a transient, we got a steady state. Next class, we'll come up, do some end-of-course business, work this out, and then look at one more application of an LC circuit. All right, we'll see you next time.